Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to discuss about the effect of temperature on rate constant. As we know, the rate depends on two things. One is rate constant, Ra equal to K Ca example Cb, and rate depends on rate constant and the concentration of the reactants. We know more is the concentration, more is the speed of the reaction, less is the concentration and less is the speed of the reaction. In similar way, the rate constant is the one that depends on the temperature. Always keeps in mind, if we continue to increase the temperature, the value of the rate constant will continue to increase. If you decrease the temperature, the rate constant value is going to get decreased. Always, whether it is an exothermic reaction or endothermic reaction, the rate constant always increases with the temperature. This is the fact. And when in today's lecture we are going to discuss about this activation, because rate constant in turn consisting of this activation energies, and there are many theories and are came in place to estimate the rate constant. Okay, let us discuss about all these things. Here you can see any particular reaction and I have representing the rate at K, Ca, Cb. Let us take it as a second order reaction. And we don't worry about this concentration term now, we worry about this rate constant term now. The rate constant, to estimate the rate constants, the three theories came in place majoritarily. One is Arrhenius theory, second is collision theory, and third is transition theory. All the three theories are used to estimate the values of the rate constants, because every rate constant consisting of one inbuilt parameter which is called activation energy, and second the temperature. And I told you rate constant only depends on temperature, and the another parameter, the K, depends on is activation energy. Okay, these are the two important factors that decides the value of the rate constant. Arrhenius says that the value of the rate constant Ka is equal to pre-exponential constant, which is K0, which comes before the exponent. It's called pre-exponential constant into exponent of minus E by RT minus delta E. Delta E is the activation energy for the reaction, that is the minimum energy required for the reactants to gain before the product formation takes place. Minimum energy you have to supply. And R is the temperature, Tr is the universal gas constant. Similarly, as per the collision theory, and then let us Arrhenius theory or collision theory, and the value of the rate constant in a collision theory is depends on T power Ka is equal to K0 dash into temperature power half into exponent of minus delta E by RT. And you can see the additional, here there is no temperature term before the exponential term. Here before the exponential term the temperature term has come, and this is because as per this theory, collision theory in sense, and because every molecule before it goes to the product, reactants, before it going to the product, it has to reach to some state which is called activated state. Okay, because for the reactants to become products, it needs to exchange some electrons between them, because energies between the reactants. So before the product formation, the reactants will collide to each other, it reaches to the activated state. From this activated state, the products will, because energy exchange of energies and atoms takes place and the product formation takes place. That's what the collision theory talks about. Collision theory in terms talks about, and not every, because how the reactant will get the energy from the collision between the two reactant molecules. If two reactant molecules collide, the exchange of energies takes place. And do you think all the collisions lead to product? No, only the collisions which require the minimum energy. Not every collision and reached energy, minimum energy will come, because there are specific collisions and specific alignment if two molecules will collide each other, the minimum energy it should attain. Not every collision will reach to the minimum energy, only few collisions will reach to the minimum energy that is required for the product formation to take place. So that is why, as per this theory, how to estimate the pre-exponential constant K0 dash means something, if you get the new terms here, and sigma A and sigma B are the molecular diameters of the molecules A and B, and is Avogadro number, and Kb Boltzmann constant, T is the temperature, Ma and Mb may be molecular weight of molecule A, molecule B. All the things you need to know to estimate the Ka. You need to know K0 dash, you need to know the temperature, you need to know activation energy also. Or if you know all the informations, then you can able to estimate the value of the Ka. Here Arrhenius theory, Ka is proportional to only exponential term. Here Ka is proportional to the temperature term as well as the exponential term. Similarly, the another theory that came in place is called the transition state theory. It is similarly kind of activated state theory. Every molecule should reach to that certain state. That certain state, after reaching certain state, the product formation takes place. That is what this hands. And Ka can be estimated by Kb Boltzmann constant, T is the temperature, H is the Planck's constant, delta S star, delta H star. That means entropy and enthalpy of the activated state. Example, if any molecule it reaches to the activated state, the activated state it has got specific entropy and specific enthalpy. That is what the star symbol is. A plus B gives rise to AB star. AB star means the molecule which is bent to this activated state. This, if you have to know this delta S star and delta H star entropy and enthalpies at this stage to estimate the value constant Ka. Here and on simple terms, the rate constant is proportional to the temperature power 1 and exponential power delta E by RT. Here it is a very simple. Here only exponential term as per the Arrhenius theory. Here as per the collision state theory, the Ka depends on temperature power half into the exponential term. Here the Ka depends on temperature power 1, now it is power 1 and exponential. This is the only basis, only difference between the three theories. All the three theories have the different backgrounds, and ultimately all the three theories are used to estimate the rate constant of a reaction. Okay. Let us discuss about a bit small further about this. If suppose a reaction that is happened, okay, reactants goes to the product. Reactants has some energy, products will have some energy. Okay, that is what this energy diagram. If you plot energy on the y-axis and molecules energy state on the example, x-axis is the reaction coordinate. Reaction coordinate is nothing but it is a very abstract term. You imagine on the left side of the x-axis is the reactant state, on the right side of the x-axis is the product state. Reactants, it has, when the molecule is going from reactant to the product stage, how the energy landscape is changing. Okay, that is the y-axis. Imagine this is, we are discussing about endothermic and exothermic. Let us discuss about the endothermic reactions. And the point which is starting here, exactly this Re is the reactant's energy, and so once the reaction happens, product is going to form. Here it is called the product energy. Here it is a reaction energy, and this end point is called the product energy. The difference between product energy minus reactant energy is nothing but enthalpy of a reaction. And if you minus product energy minus reactant energy, then it is called enthalpy delta H of the reaction. If delta H is endothermic, okay, if delta H is positive, that means product minus reactant is that means products have higher energy and reactants have lower energy. In such cases, if delta H is positive, that means because the product is at the higher state than the reactant, you have to supply excess amount of energy into the system. Okay, whenever you have to supply the energy for the reaction to happen, that means it is positive, that means endothermic reactions. And the distance Okay, you get to know what is endothermic reaction. Endothermic is such a reaction where delta H is positive. Delta H is positive means product is the higher energy and reactants are lower energy. And the another, because before the reactants goes to the products, it has to go through this activated state. The activated state, okay, without reaching the activated state, the product cannot be formed as per the theories, okay. And the difference from reaction energy to the maximum energy, see the difference, this is the reaction energy, this is the maximum energy. The difference between these two is called the activation energy. That means for reactant to form the product, you have to supply this much of energy so that the reaction happens. The energy with which you have to supply for the reaction to happen exactly this, that's called the activation energy. So for endothermic reaction also you have to supply the energy, for exothermic also you have to supply this starting energy for the reaction to happen. Now you understood? Let us go to the exothermic now. And the exothermic means the reactions in which heat will be released, okay, because of the reaction. That means reaction, RE, reactants energy, PE is the product energy. Because the reactant energy is at upper level, product energy at the lower level, that means the reactants always have large energy compared to the products, okay. Because of this reaction, reactants lose some energy to form the products. The difference is delta H is nothing but product energy minus reactants energy. When the product energy minus reactant is negative, why this is negative? Because reactants energy is higher than the products energy. So negative, whenever this negative means there is heat that comes out of the system because of the reaction. So for those kind of reactions where the heat energy will be released, that systems are called exothermic reactions, okay. Now you see here, from the reactant, from this point is reactants and this point is called products. Before reactants to form products, it has to go through again this kind of barrier. This barrier is called activation energy. That means minimum energy you have to provide for this reaction to happen. So that is why the delta E, from here to the maximum state, okay, from here to the maximum state, this is called the minimum delta E, that is minimum activation energy that is required for a reaction to happen. Whether it is a endothermic reaction or exothermic reaction, you have to supply the energy which is called the activation energy. And I hope you understand energies, okay, because in reality there are, if you let us, in reality there are reactions which have small energies required, activation energy is required. There are some reactions where the big activation energies are required, okay. Let us do that, okay, because with the temperature this low activation energy will behave differently and high activation energies will behave differently. In the sense, one is more temperature sensitive, and wherever the reactions where low activation energies are there are less temperature sensitive. The reactions where the higher activation energies are required are more temperature sensitive. Let us do that sensitivity part, okay. Let us take the Arrhenius equations, because Arrhenius theory is sufficient for us to analyze, because you don't have to worry about the other theories, okay. Let us take the Arrhenius theory as a basis. Let us further move into the lecture to decide the sensitivity of a temperature with respect to low activation energy reactions and high activation energy reactions. Ka is equal to K0 into e power minus e by RT. If I apply logarithm on the both sides, you get ln Ka is equal to ln K0 minus delta E by R into 1 by T. And if I see this as a equation of a line, y equal to mx minus mx plus c, y equal to mx plus c. Here the slope will be negative. Here you can see what is the slope, m is equal to delta E by R. Here y is equal to ln Ka, x equal to 1 by T, m equal to minus E by R, and c is equal to ln K0. It's a line. That means if you plot a line of y and x, you can see a line with a negative slope. What is my y? Ln K. What is my x? 1 by t. Okay. If I plot the graph between ln k and 1 by t, I can see a line with a negative slope. The one which is on the blue, that is called low activation energy, low delta E by R. The one which is on the black, that is called high activation energy. Less is the slope, that means low is the temperature sensitivity. Greater is the slope of the line, that means high is the temperature sensitivity. Low activation, low delta E by R means low activation energy, low slope means low delta E, high slope means high delta E. Now let us take one small example. The graph is plotted between ln k and 1 by t. Remember, this is 1 by t, not t, because here is 1 by t. As t increases, 1 by t decreases. That is why 200 is here, 2000 is here. It's not a 200 here and 2000 here. Okay, it's a 200 is on the right hand side, and as you increase the temperature, decrease the temperature or increase the temperature, the value, that is how it looks like. So let us see, and let us take a basis here. The blue one is the low activation energy line, and the black line is the high activation energy line. The one at a, let us say they both meet at one point, example, that is called the temperature T1. And let us see, I need to increase, let us say I have some value of K1 at temperature T1. Suppose if I want to increase the value of K1 to some other value, that means by increasing the temperature, how I am going to increase the value of the ln K1, okay, ln K1. That means more is the temperature, that is, let us say at temperature T2, okay, which is at the higher temperature, and higher temperature, what happens is, you can see the ln K1 is my starting point. From increasing the temperature from T1 to T2, my value of K increasing from ln K1 to ln K2, okay, for the low activation energy line. For the same temperature difference from T1 to T2, you can see the value of ln K1, let us say at temperature T1 the black line value is ln K1, okay. At temperature T2 the black line value is ln K3, and you can imagine for the same temperature difference, the one which is having low activation energy, the rise is only this much. For the high activation energy, the rise is this much. For the same temperature, the one with the higher activation energy, the value of the rate constant was increased tremendously compared to the one which is having the low activation energy, okay, the low activation energy. Let us say ln K2 is much greater than ln K1 for the low activation energy, but ln K3 is much greater than ln K1 because of the high activation energy. So that is what the temperature sensitivity. That means in reactions where the high activation energy reactions, and the value of the rate constant increased tremendously compared to the low activation energy values. And let us go to the try to solve one example. Let me give you a small clarity on this graph, and because people still might have confused. The graph is 1 by t, that means in denominator the temperature value is increasing, that means the value will shift towards the left, okay. When the temperature value is low, that means the value is here, that means low value of the temperature, okay, low temperature is here and high temperature is here, okay. Don't get confused with this, because higher is the temperature, the value will be here, okay. Lower is the temperature, the value will be here. That is why even though the 1 by t is lower, it is shown as 2000 Kelvin here, because lower is the value of 1 by t, that means I am talking about the high temperature. Higher is the value of 1 by t, that means this side, that means I am talking about the low temperature, okay. Let us try to do and solve a problem. Let us take the small example, like there is a first order reaction happening, the same reaction, one we will try to solve with low activation energy value, and the another problem we are trying to solve with the high activation energy value. Given the problem is, the problem it is defined in such a way that to increase the rate constant value to 10% more, how much temperature I have to rise. You know, from the Arrhenius relationship, rate constant will changes with temperature. Temperature increases, rate constant increases, temperature decreases, rate constant decreases. And let us see from a base value, let us say from what temperature I have to rise to increase the value of rate constant to 10 more percentage, 10% more. So, let us take the value delta is given 200 calorie per mole, low activation energy is, and R equal to 1.98 calorie per mole Kelvin, temperature equal to 25 degrees centigrade. That means this is my starting point. Pre-exponential constant K0 is equal to 4.2 into 10 power minus 5 per second. Now, calculate the temperature required to increase the rate constant value by 10%. Let us use the equation Arrhenius relationship. K is equal to K0, K means Ka, rate constant of A, e power minus delta E by RT. At 25 degrees centigrade, you apply this formula. I know K0, I know the delta E, I know R, I know temperature. That is, at 25 degrees centigrade, the value of the rate constant is K1. K1 is equal to K0 into exponential minus E by RT. If you substitute the respective temperatures and R and activation energy values, you get the rate constant value is 2.99 into 10 power minus 5 per second. Because we are talking about the first order system. For first order system, the rate constant, units of the rate constant is 1 by second. And at what temperature my K2, that is my new rate constant, is 10% more than K1, that is 1.1 times K1. I know at temperature what K2 is equal to K0 into e power minus delta E by RT2. If I apply the logarithm, ln K2 is equal to ln K0 minus delta E by RT2. From this, keep temperature on, take the temperature on the left hand side, rest every time on the right hand side. That means T2 is equal to delta E by R into ln K0 minus ln K2. What is this K2? K2 is 1.1 times K1, okay, 1.1 times K1. Then you substitute the values of K0, delta E, R and K1 in this equation, you get 404 Kelvin, that is 130 degrees centigrade. That means to increase the rate constant value to 10% more, you need to increase the temperature from 25 degrees centigrade to 130 degrees centigrade for this delta E, low activation energy reactions. Same problem exactly we repeat, same values for the high activation energy systems. Example, now the activation energy is 20,000 calorie per mole. Rest everything is constant, okay. K0 is, we have taken the same K0, and at temperature 25 degrees centigrade, everything remains the same. So, at 25 degrees centigrade, the K1 you have to estimate. You know, K1 can be estimated by K0 into e power minus delta T by RT1. Now, you have to given K0 is equal to 4.2 into 10 power minus 5, exponent of 20,000 divided by 1.98 into 298. For this, you get 1.2 into 10 power minus 10, the value of the rate constant is 2.2 into 10 power minus 10 per second. This is at 25 degrees centigrade. Our job is to find out what temperature I can increase my rate constant to 10%. Similar way, K2 is my new rate constant is equal to 1.1 times K1. Similarly, everything the formula remains the same. Now, you apply, you substitute each and everything and times K1. Now, the value is K1 will be changing. Here the value is K1 is this one, and here the value is K1 is this one. K0 everything remains the same because it is a pre-exponential constant. So, finally, the temperature you got is 837.2 Kelvin, that is 564 degrees centigrade. That means, for high activation systems, high activation energy system, to increase the value of the K2, you have to increase the temperature from 25 degrees to 564 degrees. For low activation energy systems, to increase the temperature from 25 to only 130 degrees centigrade is enough. This is called the temperature sensitivity, because high activity energy are more temperature sensitives, low activation are less temperature sensitives. the kind of, I hope you understand and the essence of rate constant and its measurements and various theories, the equations proposed from various theories. Okay. Thank you very much. Let us meet up with a new lecture. See you soon.